Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a new concept in chemistry, and that is the concept of radioactivity. But understanding the concept of radioactivity will require the understanding of the role of the nucleus as a subatomic structure. Now that we have discussed that one in one of our videos, I'm going to have a short recap for us in order to understand what different aspects of the nucleus play a role in order to come up with this concept, of course, of radioactivity. So first, I'll try to look at a small recap of what the atomic structure entails, and then from there we will try to look at how the concept of radioactivity has been developed over time. So for that case, thank you and welcome. So therefore, as I've said, our topic of discussion for today is going to be the concept of radioactivity. And as I've said, in order for us to understand this concept of radioactivity, we're going to look at a small recap on the concept of an atom, which is going to lay for us a basis in understanding how the process of radioactivity works. Now, this stems from the fact that radioactivity entails basically a subatomic part of an atom, that is the nucleus. So therefore, it's fundamental for us to understand how this nucleus play a role in developing this concept of radioactivity. In this case, of course, we are going to look at this part of matter that we are calling an atom. Now, this concept of an atom developed over time from the time of Democritus. This is in Greece, of course, at that point in time. So this was long way back. It's around that's around 2 millennia. No, that's around that's around 2 millennia ago and a half. It's quite a long time, and this point in time, we discovered that there were very minimal ways in which maybe philosophers and our natural philosophers at that point in time could be able to do some things like scientific methods, which basically rely on experiments to try and interpret natural phenomena. So therefore, in them, to understand the concept of things which of course could not be seen due to from our naked eye perspective, it was difficult. But Democritus came up with the concept of a unit of matter that he called an atomos, which in actual sense at that time, or from the Greek perspective, meant indivisible. So therefore, he said that there's a very fundamental part of matter that cannot be divided any further, which he called an atomos. So this is where the concept of an atom came from, and over time different scientists came with different perspectives on how to interpret this concept of an atom. So therefore, we're going to look at some relevant examples which are going to assist us in understanding the structure of an atom over time. So that one is going to lay a basis for us in understanding the concept of radioactivity. So the first one we are going to look at is the concept of John Dalton, who came up with different postulates to try and interpret the concept of an atom. Of course, this is a Dalton's atomic theory, which said that elements are made up of tiny particles, which are called atoms. So therefore, his argument was that elements are made up of tiny particles, which he called atoms, of course from the concept of Democritus. And he stated that atoms of an element are identical but differ from those of other elements. So in this case, he was trying to refer to the similarities of atoms of the same element. And then he stated that so atoms of an element are the same or similar. And then he stated that in a chemical reaction, of course, when a chemical reactions occur, the rearrangements happen in a way that there's conservation of course of atoms. And this one, of course, is going to be seen when we're talking about the stoichiometry of chemical equations, or stoichiometry in actual sense. So in this case, of course, he is postulate also argued that atoms of different compounds or different atoms form compounds in constant ratios. And this is the concept of course, stoichiometry that I've talked about. So Dalton's postulate brings us some light in a sense that he argued that atoms of the same elements are similar. So therefore, we're going to look at the concept of isotopes and others which are going to come later. Now, there's also an argument that was made by J.J. Thomson. This is another, of course, English physicist who came up with the concept of what we call the electrons. So J.J. Thomson came up with the concept of electrons. And in actual sense, he argued that electrons have a negative charge. And this he confirmed it using the cathode ray tube in his experiment to confirm that the electrons are indeed negatively charged. So in that case, he came up with also the mass, that is the charge to mass ratio for electrons. And J.J. Thomson's work led him to a conclusion that atoms are made up of what we call the plum pudding model. That atoms are made up of a structure that is known as the plum pudding model. And he argued that electrons are dispersed in a uniform positive charge. So suppose this is a positive charge that is uniformly distributed inside there. Now that the electrons are negatively charged, Thomson's argument was electrons are dispersed in a uniform positive charge. And this, of course, formed a basis at that time for having a different way in which we could look at atoms. And then there were further experiments that were done, of course, when there was an advent of some scientific methods which were being developed, of course, to try and confirm the arguments of these earlier scientists or trying to dismiss some of their claims. So in this case, of course, there was an experiment that was performed by an American physicist, that is Robert Milken. So in this case, Robert Milken's argument was that, so in this case, his experiment enabled him to measure the charge of an electron using what we call an oil drop. So this is what is famously known as oil drop experiment, which he used to measure the charge of an electron. And therefore he concluded that the charge of an electron from the measurement is that value, that's 1.6 times 10 negative 19 coulombs. And he also measured the electron mass, which is going to be 10 negative 31 kg. So this was the work of Robert Milken. So in this case, of course, we're going to see that the aspects of mass and charge of an electron have an influence on the structure, of course, of an atom. And we're going to see that one shortly. And then later there were some of the experiments which were performed, of course, which laid a basis for the current understanding of an atom. And these were the experiments that were done by, of course, Ernest Rutherford. Now, Rutherford performed an experiment which led him to a conclusion that there are positive charges inside an atom. And he said that the positive charges is not like a plum, it's not like a pudding. Now, if we see that the argument that J.J. Thomson had said that the positive charges are distributed in an atom, I mean, electrons are dispersed in an atom in a sense that they are assuming this nature in positively uniformly distributed charges. Now, Ernest Rutherford's argument was that the positive charge is not like a pudding or the plum pudding that we have illustrated, but is concentrated in a nucleus, which he showed using the alpha particle experiment, whereby he used the foiled leaf of gold in order to perform experiment. And he discovered that whenever the particles that were incident on that gold leaf there was a characteristic way in which they were being dispersed, and he therefore concluded that most of the atom is an empty space. And this, of course, led him to the conclusion also that at this point of an atom, there's what we call a nucleus. The nucleus at the center of an atom is a nucleus, and Rutherford, together with James Chadwick, discovered that the nucleus has no charge, therefore it is neutral. So this is together with that is Rutherford and Chadwick made a confirmation that the nucleus is indeed neutral. Therefore, this is going from the time of Democritus to this point. We are trying to see some of the arguments and confirmations which are being done using experiments by different scientists. So in this case, we are going to look also at the modern understanding of an atom by looking at the works of the later scientists, which of course relied heavily on what had been discovered before and trying to confirm the arguments or either dismiss them. Now in this case, there was this Moseley, Henry Moseley. Henry Moseley's argument was that each element contained a unique number of protons. So this unique number of protons for each element, so this unique number of protons for each element is what we call the atomic number. This is the atomic number of elements that Moseley was trying to propose. Now the later work of Niels Bohr and of course the work of Niels Bohr and of course other scientists who had come before him complemented what we call different structures or models of an atom that we of course know today. And each of them of course are going to shed light on how the smallest or a part of the indivisible part of matter that Democritus had argued, how it appears or how its structure of course works. And then we are also getting some information that can assist us to try and understand the different behavior or characteristics of atoms of different elements. Now Bohr argued that electrons orbit a nucleus. So therefore there's a nucleus that was confirmed by the alpha particle to be centrally located in an atom. And therefore Bohr argues that the electrons orbit the nucleus. And in this, of course, the model of an hydrogen atom is based on this that we have discussed in one of our videos in chemistry. So in an essence, this one gives us the basis for understanding the concept of an atom. And of course, later works, which of course rely heavily on modern physics, or modern chemistry, basically modern physics on the theory of quantum mechanics, provides them the wave mechanical model of an electron, of an atom, of course, which argues that electrons act as particles and waves, and therefore giving the concept of what we call orbitals, which are probability in space where we are likely to find an electron. So this argues that an electron, of course, behaves like a wave, and therefore it is not possible for someone to just a time or just a point where a wave can be located, therefore giving the concept of orbitals. Now, having given that small recap or historical development of the concept of an atom, we're going to look at the different ways in which we can be able to represent this concept of radioactivity using the basic knowledge that we have attained from this concept of an atom. Now, an atom basically consists of different. So in this case, in radioactivity, we are going to look at the role of the nucleus, which is a subatomic part. But therefore, we are going to look at an atom, as we have said. This is where we have left from our small recap, and this is the nucleus. Now, in this case, of course, the from the experiments that have been done, the electron is negatively charged. This is negatively charged. And then the nucleus consists of other subatomic particles, that is the protons, which are positively charged, and then the neutrons, which of course Jadwick and the other Jadwick and Rutherford confirmed that this basic atomic part of matter, of course, that is Rutherford and Jadwick, confirmed that the nucleus has no charge. And Rutherford's experiment had confirmed that the nucleus is centrally located, therefore leading to Niels Bohr's argument that this is the model of an atom. So therefore, as I've said, these are some of the subatomic particles: the electron, the protons, and the neutrons. And we're going to see that the protons are positively charged, and they are found in the nucleus, and therefore they are surrounded by negatively charged electrons which orbit around the nucleus. Now in this case, of course, when we were trying to see the Milken experiment, we saw that Milken was trying to propose the quantity for charge, of course, of an electron, which is said that it was 1.6 times 10 raised to power negative 19 coulombs. And they measured also the charge to mass ratio. Now in this case, we're also going to see that the mass charge ratio for these specific subatomic particles is going to play a fundamental role in trying to develop up this concept of radioactivity. Now I'm going to illustrate these different aspects of the three subatomic particles that I've listed, so that we can be able to understand what role they play in this concept of radioactivity. So I've listed different, all the three basic subatomic particles that we have discussed. So therefore I'm going to use the specific figures here to try and do a comparison, or try to show the different characteristics of their, of course, mass in relation to the charge. So therefore for protons, the relative mass is 1 and 1 to the nucleus, and to the neutron. But for the electron, the mass compared, so this is the relative mass means comparison with the others. So therefore the relative mass for electron is seen to be very small, which basically implies that much of the mass of an atom depends on the protons and the neutrons. So therefore for this charge, we have mentioned that the protons are positively charged. These ones consist no charge, and the electrons are negatively charged. So these are some of the basic properties that we're going to see, which are going to take as sort of give us a clue on how these subatomic particles behave. So as we saw from the Mosley's argument was that atoms of the same elements have the same number of protons, and therefore we're going to see that there are different ways in which we can be able to interpret atoms of different elements, which is going to lead us to the concept of what we call isotopes. Now, isotopes, elements can appear in different forms depending on the ratio of the protons, the neutrons, and the protons and the neutrons basically need structure, and therefore this gives us the concept of isotopes, whereby isotopes are forms of an element's atom with the same number of protons but different number of neutrons. Now we're going to use a symbol to represent the different numbers that we have talked about, which are going to give us a concept of an isotope. So these symbols are going to be significant because as we go ahead, they are the ones that we're going to rely on, basing the argument that we have already discussed, what each of them will have represented. So this basically represents, or has a general, gives a general representation of what we call an element. So therefore this element is going to be represented using this symbol that we have written X. And then at these specific points, we are going to have atomic mass numbers for A, which is the number of protons and neutrons, now that we have discussed that these are the contents of the nucleus of an atom. And then we are going to see that Z, the number that's going to appear at this point, is the atomic number, which represents the number of protons in that particular atom. Now the behavior of these two different numbers, or maybe the value of these two different numbers, is going to influence whether an atom is radioactive or not. Or there's going to be a specific range of elements with different ratios between A and Z, which is going to determine whether an element is radioactive or not, or gives the concept of stability of that element. Now we're going to see, for instance, there's an element. I can just give an example of an element, carbon. It's given by that symbol, and then we have that is the number, of course, of the protons plus the neutrons for carbon, and then Z, which is the number of protons, is going to be, of course, 6 for carbon. So therefore, we're going to represent carbon using that kind. So these are the number of neutrons and the number of the atomic number. This is the protons plus neutrons, and therefore we can find the number of protons from trying to find the difference between the two. Now, as I've said, Rutherford is, of course, a concept played a significant role in understanding the role of the nucleus, and therefore we're going to use this one to try and determine how different elements behave, whether they are radioactive or not. So in this case, as we go ahead, we're going to be referring to this kind of representation for an element as a nuclide, which basically is going to refer to the nucleus of an atom characterized by these numbers, that is the atomic mass number and then the atomic number, which is A and Z, which is going to give, of course, different values. Or maybe we can regard the nuclide as an atom to which such a nucleus belong. So in this case, we are going also to look at now a different aspect. Now that we've looked at the different representations in which we can be able to give elements. So from general concepts in chemistry, we know that atoms, of course, or from chemical reactions, we know that atoms either gain or lose electrons to gain stability. Of course, there's a concept we talked about, the octet rule, for maybe compounds and elements, whereby we say that atoms are the extreme parts of the periodic table, right and left. Maybe they either gain or lose electrons in order to gain stability. Now, in this case, of course, we have different ways in which we can refer to atoms. Of course, we have said that the ones that can either gain or lose electrons are not stable. But we have neutral atoms, which are basically have the same number or have the equal number of protons in its nucleus and electrons in orbit about the nucleus. So therefore, this is what forms the basis for chemical reactions. And now for this kind of elements, we're going to see that a given element can have several values for A, which we have of course said, and now which implies that the number of neutrons can vary. Now I'm going to give a demonstration to show this particular statement, whereby we're going to see that different numbers of these elements, of course, we have talked about the nuclide. Now, in case we have an element with different nucleides, then we are going to have what we call an isotope. And of course, an isotope, as we have said, is an element that has got the same, can have the same, of course, atomic number, but different mass numbers. For instance, I give an example here of carbon that I had given, which has got 6 protons and therefore 6 neutrons. But we have different nucleides for carbon, which is carbon 12, carbon 13, and carbon 14. So in this case, if we try to look at the number of the subatomic particles for these different nucleides that are written on the board. Now for protons, the first one consists of 6 protons, and the second one 6 protons, and the other one 6 protons. And then for neutrons, Now we said that the total of these two form what we call the atomic mass number. So therefore we're going to have 7 for this, now 6 for this first one, so that they can make a total of this. And then the second one also is going to be 6. But the third one is going to be 8. So the total between this and this forms what we call atomic mass number. In this case, the number of now nucleons. Nucleons basically refers to protons plus neutrons. So therefore this is going to be 13. I mean, the first one is going to be 12. The second one is going to be, of course, this one forms 7 actually. For the neutrons is 7 neutrons. Therefore the nucleons will be 13. And then for this one, it's going to be 14. So in this case, if we try to look at this, there's the concept, when we're trying to learn about the concept of atomic mass, this element carbon-12, which is an isotope, is in terms of abundance, it's very abundant in nature, so it's around 99% of these isotopes, and this one's abundance is very minimal, and this one is very small. So in this case, of course, this one gives it a characteristics of being used as a reference element when we are trying to talk about atomic mass of other elements. So in this case, this one gives us a basis for trying to understand the concept of radioactivity, in a sense that the different numbers of protons and neutrons which form the nucleus dictate on how these elements are going to be stable. So remember, we are floating one of the concepts in physics, of course, about the nature of forces, and this is the Coulomb forces, or the Coulomb law, which dictates about the concept of repulsion and attraction. So therefore, there's bearing in mind that the nucleus consists of positively charged protons and negatively charged electrons, which are orbiting. I mean, the nucleus consists of positively charged protons and then the neutrons, which have got no charge. The presence of different positive charges which are concentrated at the center will, of course, obey Coulomb's law, whereby these charges are trying to repel from one another. But in an essence, we have what we call the nuclear forces of attraction, which try to keep this nucleus in shape. So therefore, if there's an imbalance between these forces of attraction, of course, and the forces of repulsion that are being experienced due to the negative, to the positive charge in the nucleus, there's going to be a instability. So therefore, when elements experience different ratios for the protons and of course the neutrons, there's going to be instability, which will lead to this element or a nucleus either disintegrating to attain stability, or maybe trying to keep the balance between those that ratio that exists between the protons and the neutrons. So therefore, if the neutrons are more, it's going to tend maybe to cause a disintegration in this nucleus in order to attain stability. Or maybe if the forces that are attracting, that are trying to cause a repulsion between the positive charges in the nucleus are more than expected, or are having an imbalance, therefore it's going still to be unstable. So this leads to the concept of radioactivity, in a sense that there are some specific elements which naturally undergo a spontaneous disintegration process in order to form stable ones. Now this one leads to the release of energy. So in a sense, I'm going to put this one here. So the instability in the nucleus that is caused due to imbalances in forces leads to what we call nuclear instability. Now that we said most of the elements, or maybe the particles, tend to attain or stay in that of course, the low energy state whereby they are stable. So in this case, of course, we're going to see that the instability in the nucleus that is caused by the different forces that I've explained leads either to disintegration of those nuclides in order to attain stability. So in this case, this is the concept that we're referring to as radioactivity. And this radioactivity can be defined as spontaneous. This is a spontaneous disintegration of non-stable atomic nucleus to form stable ones. This process is accompanied by a release of energy in form of electromagnetic radiation, and of course some parts of what we call either the energy or particles. So we are going to see different types of energies or disintegration products which are formed in one of our discussions on radioactive decay. So as I've said, this one, the discovery of an atom and different parts and behavior of an atom has led us to the discovery of a different way in which we can be able to look at the subatomic structure. Of course, that is the nucleus, which is undergoing instability and forming another process that we've called radioactivity. So in an essence, that is the concept, of course, guys, that I was trying to talk about. So this is a concept that lays a basis for us in understanding, or it's going to be a prerequisite for us in understanding other topics which we're going to discuss concerning radioactivity going ahead. So that is it for today, guys. Thank you. Bye. God bless.